Here's a question to work on right away here. We've got a river, and in this river, we've got a current going 7 meters per second to the east. We're heading across this river, or aiming across this river at 12 meters per second, and this river is 100 meters wide. We have 3 questions that go along with this question. We want to find out the velocity of the boat, or whatever it is that's going across the river, relative to the shore. We want to find out how long it takes to cross the river, and we want to find out how far downstream this boat ends up going. Of course, if you head directly north across the river, but there's a river current that's going to the east, you know you're not going to end up directly across the river, right? You're going to end up somewhere northeast, right? How far downstream do you end up going? All right, that's the question. I'd like you to take a look, definitely yourselves, take a look at question A right now, and then we'll see how question B and C are going for you, and we'll take a look at those ones as a group. All right, let's have a look here. Question A is straightforward, at least compared to the other 2. Question A is very much like some of the questions that we've done already. Let's draw the vector diagram for question A, where it says, what's the velocity of the boat relative to the shore? We got 2 vectors, both solid line vectors here, because they both contribute to where this boat actually goes. Neither one of them are where the boat goes. They both contribute to where the boat goes. So let's draw the first one. We're heading to the north at 12 meters per second, and we've got a current that goes to the east at 7.0 meters per second. Where do we end up going? Where do we really end up going? Well, that's the resultant vector, the dotted line vector that goes from start to finish right here. Let's find the value of that resultant vector by saying the square root of 12 squared plus 7 squared. 12 squared is 144, 7 squared is 49. I think it's square root of 203, I think. What does that end up equaling? 13.89 meters per second, which is rounded to 2 digits, 14 meters per second. So this boat, although it's aiming at 12 meters per second, without the aid of a river current, it can only go 12 meters per second. But with the aid of the river current going to the east here, it's able to travel at 14 meters per second. What angle does it end up going at? Well, let's say theta is equal to the inverse tan of opposite over adjacent, 7 over 12. And what do we get for theta there? 30.2 degrees, which we're going to round to 2 digits, 30 degrees. The reason that I'm expressing unrounded numbers here is because I may need to use those later on, right, for question B and C. So here we got 30 degrees, and this would be west of north, because we're measuring it from the north, and then, east of north, from the north, but we're going east from the north. All right, we can always measure an angle from either north, south, east, or west, and this one is measured from the 12 meters per second to the north. So there we go. Where do we end up going? Where's the velocity relative to the shore? We're at 14 meters per second at 30 degrees east of north. Now comes the tougher question. How long does it take to go across the river, and how far downstream does this boat end up going? Anybody have a suggestion for this? Alex? $100 meters across the river? Okay, so you're saying use V is equal to delta D over delta T, right? Rearrange that to solve for delta T equals delta D over V, right? And then we're going to say 100 meters divided by 14 or 13.89 meters per second, right? How many people agree with that? Okay. That's what almost everybody would say the first time that I would ask them, but it's not correct, although you're definitely on the right track. Here's what's wrong with this. What am I going to replace that with? What do I replace that 13.89 with? With 12. Why? Well, think back to day 2 of Physics 20, when we introduced V is equal to delta D over delta T. On day 2, we recognized that the displacement and the velocity must be in the same direction. Right? When you use this equation, velocity and displacement are always in the same direction. So when we're using it in a completely different context like we are right now, the same rule applies. the displacement and the velocity must be in the same direction. So it's okay, Alex, if you're going to use that 14 meters per second or 13.89 meters per second right here, that's the hypotenuse. But if you do, you must use the displacement across the river at that angle as well. And we don't know what that is. So it's rather than finding that, when we could find that, because we do have the angle now and we have the 100 meters across the river right vertically, we could find that hypotenuse for the displacement and use this displacement and use this velocity. But easier, I would suggest, is to, if the rule is to be consistent, use the same direction of velocity as displacement, than to use this displacement and this velocity. Make sense? You can use whatever velocity you want, but you have to use the displacement in the same direction. So we're going to say 100 divided by 12 because that's the one that's most convenient for us. 100 divided by 12 would be 8.333. 8.333. So that's how long it takes to go across there. Does that make sense, guys? Alex was correctly observed that we're going to use this equation. Perfect. Okay. It's just a matter of recognizing that we have to use the velocity in the same direction as displacement, and that will be always the case, no matter what the context is, whether it's that day 2 question that we had, or whether it's this question that we have that's completely different context, or whether it's some other completely different question. What about C? Now that I've corrected all of you guys that put up your hands on that one for B, how do you think I'd do C? You can nail this one now. Probably couldn't have before, but now you can. No, it's not going to be 100 divided by anything. Yes, sir? Well, you could, yeah, you could. You could use the 100 and then the angle, instead of using a triangle for velocities, use a triangle for displacements, and then find this side of the triangle for displacement. Same angle, right? You can do that. Yeah, that works. It's not the way that I was going to do it, but that's fine. Of course, if you made a mistake with the angle, then you're wrong, but it's still a good way to do it. Here's the way I was going to do it. I was going to say V is equal to D over T again. Rearrange it to solve for D, V times T. If I want to solve for the displacement downstream horizontally, what velocity do I use? 7 meters per second, right? Because the velocity and the displacement must be in the same direction. Displacement to the east, well, I'll use the velocity to the east. What time do I use? 8.333, the only time that I have. Why am I allowed to use the time for this component and this component, but I'm not allowed to mix and match the velocities or displacements? Because time's a scalar. Velocity and displacement are vectors. So you got to be consistent with those. Time, use it wherever you want. 8.33 times 7 would be 56. A third of 7 is, I don't know, I'm going to say 56.2 or something like that. 58.3, all right. We're going to round that to 2 digits, 58 meters. 58 meters downstream. Got that? Question A, exactly the same as the questions that we've done up until this point. Okay, probably get a question like that, right, on a test on next Wednesday. Question B, hey, who knows? But I really like question B and C. I really like question B and C because it takes it to that next level, right? It's that typical question of aim this way, wind this way, or river current this way, and then we got to do something, a little bit of something with that, okay? And we got to remember some of the rules and go back to the second day of Physics 20 and really like questions like that. So you never know what you might see with something like that coming up on a test on Wednesday. We good there? Big thing to remember with question B and C, right? Big thing to remember is just velocity, displacement, whichever one you're using, okay, whichever X or Y or angled or whatever, doesn't matter, but just be consistent between velocity and displacement. If you're using X velocity, great, use X displacement. If you're using Y velocity, great, use Y displacement. If you want to use the velocity at the angle, great, use the displacement at the angle. They always have to be in the same direction. All right? Let's take a look at question number 5 on your worksheet right now. Let's take a look at the worksheet question number 5 here now. It says the captain of a ship aims his ship at a velocity of 25 meters per second directing north across the river with a river current flowing at 8 meters per second to the east. So here's my river. Okay, he is aiming at 25 meters per second to the north, but there's a river current that's 8 meters per second to the east. The river is 850 meters wide. It's pretty important actually in these questions to put in your units. Sometimes we get a little bit careless, a little bit lazy, and we don't bother putting in our units, but it's pretty important here to do that. And the reason I say that is because with these questions, we got 2 different sets of units, right? We got 850 meters, and then we've got this 25 meters per second. And what we don't want to do is combine those 2 pictures. We can't say 850 and 8 in the same diagram. If you draw a picture, a triangle, with the 25, it's got to be with the 8, or with the 850, it's got to be with the displacement to the east. Okay, you can't say displacement and velocity in the same vector diagram. All right, my resultant vector, which is what I'm looking for in question A, the velocity relative to the shore, is going to be r and theta. We're going to say r is equal to the square root of 25 squared plus 8 squared. What does that equal? Looks like 26 meters per second, and that would be at an angle of 18 degrees, and that would be east of north. Had you drawn it with the 8 first, then the 25, then you would have got an angle of 72 degrees, but it would have been expressed north of east rather than east of north. Question B says, how long does it take the ship to cross the river? How long? Well, we're going to say V is equal to delta D over delta T, right? Rearrange to solve for T. The T goes up by multiplying, the V goes down by dividing. Basically, they swap places. Displacement, the only displacement I have here is 850 meters. Alex, what velocity do I have to use with that 850 meters directly across the river? I got to use the 25. Good. I'm welcome to use the 26, the unrounded version of the 26 meters per second, but if I do that, then I have to use the displacement diagonally across the river as well. And I don't know what that is. We could find it using the triangle that we have here, but I would suggest that just using these 2 numbers is probably the easiest. Do the math there, works out to be exactly 34 seconds. Now question C says, just like in the last question we did, how far downstream do we end up going? Well, if we're looking for how far downstream we go, let's rearrange d over t again to solve for displacement. Get v times t. If we want to find out how far east we go, Logan, what velocity am I going to use? 8, right. Because we want to use the velocity that's consistent with the displacement, in the same direction as the displacement. It's okay to use that 34 seconds because somebody told me earlier, Jonah, I think it was, told me, it's okay to use the 34 seconds for both horizontal and vertical because time is a scalar as opposed to velocity and displacement. Do the math there. That works out to be 2.7 times 10 to the 2 meters across or downstream. 272, but rounded to 2 digits, it would be 2.7 times 10 to the 2. Good there? All right. We're going to shift gears a little bit and start the last topic of our unit and hopefully get far enough on this that we can complete your assignment for Monday. It's called projectile motion. It's related to what we've just been doing in the sense that there's vectors and angles and x components and y components, but the method that we're going to use to solve these problems is not the same at all. I shouldn't say not the same at all. In some aspects the same, but in some aspects different. First of all, let me tell you what a projectile is. It's an object that moves through the air under the influence of gravity. So if I toss a ball up in the air, if you're a football player and you toss a football, that football is a projectile. If you kick a soccer ball, it's a projectile. If you're riding your bike across the street and you jet out into traffic and somebody hits you, then you're a projectile. Anything that moves through the air under the influence of just gravity would be considered to be a projectile. Every single object that is a projectile assuming it's experiencing just gravity, no air resistance or anything like that, every single object would follow a path called a parabola. How many of you guys have heard about parabolas in math class? In math class, you usually draw a parabola like this, right? Right? What's the path of a projectile? A flipped over parabola. It's still a parabola, right? Y is equal to negative x squared, one is equal to positive x squared. They're still both parabolas. If you're not in Math 28, you haven't learned about parabolas, that's okay. It's not the end of the world. Just remember that that shape is called a parabola. And when you do it in math class, you're going to have a little bit of a head start on parabolas because you'll know roughly what it is. Now, this is really important, what I'm about to say. When an object follows a path like this, a parabolic path like this, by the way, you see parabolas all the time, not just in objects, projectile motion objects, but structural things. Okay? You see a bridge, a suspension bridge. You guys ever seen a suspension bridge where, like, here's the bridge, and then you got these two big posts right here, and then you got this cable that goes down like this, right? And then these cables are going like this. You know what I'm talking about? That's a parabola. Okay, that shape is going to be a parabola. You ever see two power poles like this, and then the wire hanging down in between them? Another one over here, wire hanging down like this? That's a parabola. Exact same shape, different proportions, but the exact same shape as a projectile has. Flipped over. It's important, it's really important to note in this parabola, when you get an object in projectile motion, it's important to note that there are two components. Clearly, the object is going up and down, but the object is also going horizontally. There are two components, the x component and the y component. And the x component is always experiencing constant velocity, not speeding up or slowing down horizontally. That's a little bit weird. Okay? We know that as an object goes up into the air, it slows down, right? But as it goes up into the air like this, as a projectile, it slows down vertically. Notice, watch my finger right now. Notice my finger as it slows down vertically is not slowing down horizontally. This way, it keeps going horizontally. Make sense? And why is that the case? Because there's nothing to slow it down. As I throw the ball up into the air like this, what slows it down vertically? Gravity. What slows it down horizontally? If there's no air resistance, nothing. And if there's nothing to slow it down, then it's going to keep going at a constant velocity. Therefore, when we're analyzing the x component, we're always going to use the equation v is equal to delta d over delta t. Always. You're going to basically treat these as two separate problems, an x component and a y component. And the x component will be v equals delta d over delta t every single time, because it's always constant velocity. The y component, it experiences acceleration because of gravity, right? And there are a number of equations that we can use to describe the y component, including d is equal to vit plus 1/2 at squared, and all of the other acceleration equations. The reason I'm writing this one down and not the other ones is because far and away, this is the most common one that you'll use. D is equal to vit plus 1/2 at squared. So although the other acceleration equations are all valid, please try this one first. You must do this one for the x component, and you will almost always use this one for the y component. But if it doesn't work for something, then you can always try your other acceleration equations as well, because just like in any acceleration problem, they're all valid. I'm just telling you to do this one first because it just works out that it almost always works for us. All right, here we go. page 107, head smashed in buffalo jump. How many of you guys have ever been to head smashed in buffalo jump? So here's this. Here's the way this thing works. It's this World Heritage site, and it's less than 2 hours away from here. And it's pretty neat, actually. They've got this big museum on the side of the hill, and basically, the significance of it is this: 6,000-ish years ago, Blackfoot people needed to eat. What are they going to eat? Well, there's lots of bison in the area. Not now, but there used to be lots of bison in the area. So let's eat some bison. Okay, we get fur from the bison to keep warm. We get food from the bison. Let's eat the bison. But bison are big animals. They're hard to kill. And you know what? There's a lot of them. We want to kill a lot of them. So what do? It's ingenious. Here's a big cliff. Bison aren't the smartest animals in the world, by the way. So you can trick these bison to all run together in a pack right over the edge of the cliff. And then they die. That's it. That's it. We trick them into running over the cliff, and then they die. That's why we call it head smashed in buffalo jump, because the buffalo jumped off the cliff. I think the significance of the name head smashed in, I think, don't quote me on this, I think actually comes from a legend of a young boy, I think, that ended up being below the cliff and got his head smashed in when the bison landed. Does anybody know if that's the case or not? Okay. It is? Okay. I used to think it was the bison getting their head smashed in, which they did. The true story is a little sadder, I guess. So anyways, these bison are jumping off the edge of this cliff. Here's the cliff, right? Here's the cliff. These bison, let's draw a picture of these bison. Since you guys saw earlier my artistic ability. There it is. He's happy because he has no idea he's about to run off the edge of a cliff. And we're gonna put a little red pom-pom on him because he says, have you guys ever heard of the variety of buffalo called the red-tailed buffalo? That's what this one is. It's a red-tailed buffalo. Okay, red-tailed bison, red-tailed buffalo. Okay. Look that up, and learn all about the red-tailed buffalo. Okay, do that tonight. Google it tonight. Red-tailed buffalo. Got it? Write that down and Google it. Red-tailed buffalo. All right. Anyway, this red-tailed buffalo is going over this cliff 20 meters high. Let's label that right now as 20 meters high. How fast is this bison, this red-tailed buffalo, moving? 18 meters per second. That's pretty fast, actually, 18 meters per second. It runs horizontally off the edge of the cliff. Look what happens to it. This is, by the way, not Wile E. Coyote. The buffalo doesn't go out like this, stop, look down, and then fall straight down. Okay, that doesn't really happen. This red-tailed buffalo will, as soon as it leaves the edge here, follow a parabolic path. Now, that's only half a parabola, right? That's because it starts at the max height already. But it's still a parabola, even if it's a half. We're going to describe the x component by using the equation v equals d over t. How come? Because every single time horizontally, the velocity of this bison doesn't change. Okay, horizontally, the velocity remains exactly the same. Now vertically, look, vertically, the velocity gets bigger, but horizontally it doesn't. So we're going to say x component v is equal to delta d over delta t. Delta d is, we don't know, do we? Delta t, we don't know delta t either. But we do know what velocity is. The velocity horizontally of this bison is 18 meters per second because it's how fast he runs off the edge of the cliff. Well, that wasn't very helpful. That's okay. Listen, don't worry about that. The strategy when you're solving these problems is write down your x component, plug in whatever you can plug in. If you get something, that's great. If you don't, go to the y component. The y component is acceleration, and we can describe that using any of the acceleration equations. But which one did I say works far and away the most often? Yeah, good. VIT plus 1/2 AT squared. So that's what we're going to try first. Let's sub in some numbers for this now and see what we get. Delta D, we know this. Delta D is what? Nope, but you're close. Neg 20 because it ends up below where it started, right? Vertically, 20 below where it started. What's its overall displacement? I don't know. Okay, because it ends up 20 meters down and then so many meters over. Hold on, let's finish this, okay? Almost done. What's VI? No. 0. Good, Kelly. VI is 0 because it's running horizontally off the edge of the cliff, right? It speeds up vertically, but initially it's traveling at 0 vertically. 1/2 of neg 9.81, because vertically the acceleration is neg 9.81, equals t squared. Let's figure out t there. For delta t here, it ends up being 2.019 seconds. Now we're going to do, hold on guys. Now we're going to take this 2.019 seconds and put it over here. What are we looking for? This displacement right here, the horizontal displacement. Now we can find it. Delta D ends up being equal to 18 times 2.019. We end up getting 36 meters. Can anybody explain to me real quickly before we wrap it up for the day, can anybody explain to me why I'm allowed to use the time for both X and Y, same time, right? But I'm not allowed to use the velocity in X and Y because time is a scalar, right? Let's go the first 2 questions. Have a look at those this weekend in addition to your assignment.